Okay, so the word cardinal has a lot of different meanings. We can talk about a sports team or two, apparently. Bird. A high position in the Catholic Church is called a cardinal. I think they're under bishops. I'm not really sure the hierarchy there, but they're up there somewhere. I mean, better than a priest.
Higher than a bishop.
Yeah.
Not a bishop.
Okay. Higher than a bishop. But anyway, lots of different meanings. So in math, it has a meaning too. Okay. We talked about the cardinal number of a set, and you'd say n of A, and with the A in parentheses if you're talking about set A. And the cardinal number is just the number of things inside the set. So if I have some set B, okay, I have 1, 2, 3, 4, 5 elements inside the set. So n of B, or the cardinal number of B, is 5. Not too bad. Okay. You just count how many things are in the set. So if you were talking about the set of all months in a year, the cardinal number would be 12. The set of all days in a week would give you a cardinal number of 7. The set of all, what's something else I know the total number? The set of eggs in a carton, 12. Okay, you just count up how many things are in there. Okay, so we're going to find the cardinal number of each of the following sets. Alright, so cardinal number of A would be 1, 2, 3, 4. Cardinal number of B, 1. Cardinal number of C, now we've got 1, 2, 3, 4, 5 numbers listed, but we have to account for the numbers in between here. So we have to do 16, 17, 18, 19, 20, and 21, so that's 6 more numbers. So it's going to be 11. Okay,
Do you have the new magic?
the cardinal number of the empty set, 0, yeah, because there's nothing in it. Okay. Okay, equivalent sets. There's a difference in set theory between equivalent and equal. Well, in math, there's a difference between equivalent and equal. Equal is when you have two things that are exactly identical, the same. So like a quarter is equal to a quarter. Equivalent is when the two things have the same kind of general value. So a quarter is equivalent to 2 dimes and a nickel. But they're not actually equal because they don't look the same, right? One's a quarter and one's 2 dimes and a nickel. So that's kind of the difference between equal and equivalent. And so when we talk about sets, sets are equivalent if they have the same cardinal number. So if their cardinal numbers are equal, they have the same number of items inside of them, then they're equivalent sets. Sort of like a quarter and 2 dimes and a nickel. So if you talked about, let's say, set A, X such that X is a day of the week has a cardinal number of 7, and B is 2, 4, 6, 8, 10, 12, 14 has 7 elements. So these two sets would be equivalent. Okay. So n of A is 7 and n of B is also 7. So far, okay? Here's some more equivalent sets. X such that X is a vowel, and X such that X is a natural number, and 3 is less than or equal to X is less than or equal to 7, which means it includes both 3 and 7, so you get 3, 4, 5, 6, 7. So what you get is, so the cardinal numbers of both sets are 5. And then these arrowheads indicate that you can pair up the elements. Now, how you pair them up doesn't really matter, but we can pair one element with set A with one element of set B, and I don't have any leftover elements on either set. It's known as one-to-one correspondence. So if set A and set B can be placed in a one-to-one correspondence, then A is equivalent to B. Okay, so that means every one element in A connects to one element in B. Okay. If set A and set B cannot be placed in a one-to-one correspondence, then they're not equivalent, and so use a not equal to C. Not equal. Now there are concepts in math known as one-to-one and onto. We're not going to talk about onto right now, we're just going to talk about one-to-one. We have to have a one-to-one correspondence, meaning there's no elements left over. And that also means that you can't repeat an element. So you can't list something twice in order to make it work. Because a 3 is only a 3, even if I list it 6 times in a set, it still only counts as 1, because it's just a 3. Does that make sense?
So instead of like 2, 2, 1, 1.
Yeah, if you had a set like that,
Yeah.
these extra 2s and 1s, this is actually that set. This only has a cardinality of 3. So if I call this set A, you don't count repeating elements. Because a 2, whether I list it once or twice or 6 times, is still just a 2. Does that make sense? So it only counts once. And that's going to come in handy here, where they did a study of the preferred age difference in a mate in 5 different countries. And those countries are Zambia, Colombia, Poland, Italy, and the United States. The green bars on the top are women, which age difference they like, and the yellow bars are men, which age difference they like. And so this is years older and this is years younger. Okay, so women like guys in Zambia that are 4.2 years older than them, but guys like girls that are 7.3 years younger.
1.3 years younger.
there's a miss there. Okay, in Colombia, girls like guys that are about 4.5 years older, and guys like girls that are about 4.5, good. Okay, in Colombia, they go okay. They meet. In Poland, 3.3 years older or 2.5 years younger. In Italy, 3.3 years older or 2.8. Oh, that's an 8. No, sorry. 2.8 years younger on both of those. And in the United States, 2.5 years older or 1.9 years younger, which that's not too far off.
America's at the end.
Yeah, America's in the end, United States. Okay, so that's our data. Now, if we express these as sets, set A is the 5 countries, and set B is the average numbers of years the women prefer the men to be older. Okay, so that's set A. And then set B, we're looking for the women's data. So I have a 4.2, a 4.5, a 3.3, another 3.3, so I don't list it because it doesn't count twice, and then a 2.5. Are these sets equivalent? Well, what's the cardinal number of A? 5, and the cardinal number of B? 1, 2, 3, 4. So the cardinal number of A is not equivalent to the cardinal number of B. So these two sets are not equivalent. Even though it came from the same data set, like the data pool, the survey that they took, we didn't end up with equivalent sets because that 3.3 repeated in 2 different countries, Italy and Poland. Okay, so a set is finite if the cardinal number is either 0 because it's the empty set, which nothing is measurable because there's nothing there, so you can measure that there's nothing. Or that the cardinal number is a natural number, some number, 4, 3, 29, 576, whatever. We can count the number of elements in the set, even if it's a large number, if it's countable, it's finite. If it ends, it's finite. Now, if you talk about cardinality that's not 0 or some set number, you're talking about an infinite set. And infinite sets, they go on forever. Okay, the set of natural numbers is an infinite set. We talk about, counting. If you think of the biggest number you could possibly ever even think of, you can always add 1 to it. And then you can add 1 to that, and add 1 to that, and so on and so forth forever. It would never end. Never ends. You can always continue to add 1 more. So that's when you get infinity, infinite sets. Okay, so what happens with the cardinal numbers for infinity, you use the Hebrew letter Aleph. Anybody familiar with that word? I have to try to draw it. I don't draw it very well. You have to forgive me. That's close. Okay. Okay, this is the number Aleph with a sub-0, and it's read Aleph null.
What is that for?
this is the cardinal number of the set of natural numbers. If you see this, so if I had, let's say, set A is the set of natural numbers, okay, all natural numbers, then the cardinal number of set A would be A with naught, infinite. I can't just use the symbol for infinity because the symbol for infinity is actually not a number, it's just a concept. Infinity is not a number because a number has a set. Like
Is it anything like equal to zeros?
infinity is actually it's actually a Mobius strip.
It's an 8. Like it was like a
It looks like a side was 8,
right.
but it's actually a Mobius strip. But it's not a number, it's an idea. This represents a number. It's a non-findable number. The cardinal number for it's an infinite set, but we say this is that number right there. This squiggly symbol with a little 0 on it, that's the number. And I said that equivalent is not the same as equal. Equal is exactly the same. Okay? So if you're equivalent, you have the same number of items in each set. If you're equal, you have the same exact items in each set. Okay, so even if they're listed differently, I could say set A is the set X such that X is a month. And then I could say set B is January, February, March, April, December. Okay. They look different. They're equal. Because they're both talking about the 12 months of the year. So in this case, I would say A equals B. So equivalent, you have the same number of items in your set. Equal, you have the exact same items in your set. All right, true or false? Are these two sets equal? Yeah, 4, 8, and 9. 4, 8, and 9, even though they're not in the same order, they're the same items. So that's true. True or false?
False.
False, because this one has that 0 added in, so it's not exactly the same. Easy enough? All right, let's move on to subsets. So we just talked about sets. You can have subsets. So we talked about, like yesterday I mentioned if you have a set of dishes and they all match, right? Well, if you think about like a set of plates that you buy at the store, comes usually with like some plates and some salad plates and some bowls and some coffee cups. Well, if you talk about the whole set of china, that would be your set. And then the plates would be one subset, and the salad plates would be another subset, and the bowls would be another subset. So these are like smaller sets that fit inside your bigger set. Does that make sense? Okay, so there are subsets and there are proper subsets, and I'll explain the difference between those. And they use two different symbols. We'll be able to figure out how many subsets are in a set, and then deal with that and infinity. Okay. So the definition of a subset. Where's my express set? Oh, there it is. Okay. All right. Set A is a subset of set B, expressed as A with the, like a kind of a squished C with a line under it. It's B. every element of set A is also an element of set B. So if I have, let's just say as an example, set A is the set 1, 2, and 3, and set B is the set 1, 2, 3, 4, 5, and 6. Okay, 1, 2, and 3 is part of set B. I just took a piece of set B and made it its own set. So that means that set A is a subset of B. Okay, if set A had 1, 2, actually let me change that, not make it set A, let's make it set C. Okay, set C is 0, 1, 2, 3. 0 is in C, but it's not in B. So set C is not a subset of B. Even though most of the elements are in there, because I added this 1, 0 in there, which is not in B, it's no longer a subset. Does that make sense? So everything in here has to be in here. You throw one different thing, and it's not a subset anymore. So like when we're talking about our dishes, and we have the plates and the bowls and the cups and everything, and that came in one box, and then I say, and silverware. That's not a subset. Got it? Okay, so is A a subset of B? Yeah. So we put that in there. Oh, and this line here is really kind of important. Oh, I forgot you don't need it on the map, but on the, yes, you do it. Okay, A, that should be B. Sorry, that's a typo on my part. Okay, so A, X is a letter in the word proof, and B, Y is a letter in the word roof. Is A a subset of B? A is the bigger one. So A is not a subset of B. But is B a subset of A? Yeah. So A is not a subset of B, but B is a subset of A. Guys, the symbols we've seen so far, we have like the squishy E, and we have the not squishy E. Okay, this is element. And that's generally talking about a single item. So like 5 is an element of the set 3, 4, 5. Okay, so we're just talking about one thing, one piece. Okay, then we have this C with a line under it, and that's the subset. Or the C with no, which is not.
On the homework, did they have just like a regular C?
Yeah, we haven't gotten to that yet. Yeah, I haven't gotten to that yet, but when I'm going to go ahead and put it on here, this is a proper subset. And I'll explain that in just a minute. Okay. And now when you're talking about a subset, it can still be a single element, like or a single thing, but it'll be in set brackets. So like here, 5 is a subset of 3, 4, and 5. If it's in brackets. But 5 without brackets, that's not a subset. It's an element, but it's not a subset because it's not a set, it's just a piece.
Yes.
Does that help?
Yes.
Okay. And then with the equal or equivalent, it's just an equal sign either way. But with equal, I'll come back to that in just one second. Equal, you'd say the set A is equal to the set B if they're both the same. Right?
When they're not equal, you put the line
Yeah. And if they're equivalent, that's when you have to put those ends on there. And this is if they have the same number of stuff. But the same number, but not the same things.
Okay.
So 5 shoes or 5 eyeglasses. But they're both 5, but they are not the exact same. Does that help?
Yes, it does.
Okay. Go back to that now, so you can write it down. You have a subset and you have a proper subset. Okay? And think about what the word proper means in like English. You know, it's exactly right? You're proper, so it's perfect. So if you're talking about a proper subset, you're talking about a subset that's an actual perfect subset. Now, if you're just talking about regular subset, so if I have the set A and the set B, and say I want to do, if A is a subset of B, and I say B is 1, 2, 3, and I need A to be a subset of B, A can still also be 1, 2, 3. Everything is a subset of itself. A regular subset. But now if we're a proper subset, a proper subset is smaller than the original set. So if my set was 1, 2, 3, a proper subset can only have 2 of those elements. It can't have all 3. It can have 1 element or it can have 2 elements. So it could be 1 and 2, or 2 and 3, or 1 and 3, or just 1, or just 2, or just 3. But it can't be 1, 2, and 3. Okay, so a regular subset can be equal. A proper subset must be smaller. That's the difference between the two. It's sort of like, remember the less than or equal to, greater than or equal to? That's what this line underneath is telling you. It's either a subset or equal to. Does that make sense? Okay, I'll give you like an actual hard example. Set B is equal to 1, 2, or 3. Or sorry, set 1, 2, 3. Okay, if I want A to be a subset of B, A can equal 1, 2, or 3, or 1 and 2, or like any combination. But A can equal 1, 2, and 3. 1, 2, 3. If A is a proper subset of B, A cannot equal 1, 2, 3. A can only equal 1, 2, or 2, 3, or 1, 3, or 1, 2, or 3. So if we're just talking about a regular subset, we can equal the original set, but if we're talking about a proper subset, we're smaller. We can't equal the original set. We have to be at least 1 element smaller than the original set. Does that help?
Can we just skip this test?
No. It's exactly like less than, or equal. It's, this one has to have less elements in it.
Okay.
This one can have less elements, or it can be the exact same number of elements. Does that help?
Yeah.
Okay, so if you, maybe when you're, it kind of looks the same, but, you know, it's the rounded one instead of a pointy one. But they work the same as a less than or less than or equal to. So if you're a subset, you can also be equal to the whole set. But if you're a proper subset, you're proper. You're not equal. You're only a sub. You're small. Does that make sense? So let's look at these examples. Subset, proper subset. If X is a person that lives in San Francisco, or X is a person that lives in California, if you're in San Francisco, are you a proper subset or a subset of all of California?
The subset.
Are you the same size or are you smaller?
You're small.
Smaller, so you're going to be the proper subset. So it's a strictly less than. If I'm here, I have 2, 4, 6, and 8. 2, 4, 6, and 8, they're the same size. So this is a proper subset, or a regular subset. Now this one is also, because it's a less than or equal to kind of a situation, but if we're just having to pick one, we're going to pick the less than, because this is smaller. Does that make sense? Oh, I didn't even read the directions, it said or both, so it is both. The empty set is a subset. You guys remember our good friend the empty set? If you're talking about any set, the empty set is a subset of every single set because nothing is inside of everything. That doesn't make any sense what I just said, but if you took every single thing out of the set, you'd still have nothing. And that's what the empty set is nothing. Does that make sense now? So the empty set is a subset of every single set in the whole wide world. And as long as you're not talking about the empty set specifically, the empty set is a proper subset of every single set. So, that's not pen. The empty set is a subset of every set. The empty set is a proper subset of every set except the empty set. So you would have to say that the empty set is like this. You can't say the empty set is a proper subset of the empty set. This is not allowed. This is okay, that's not. Does that make sense? So basically it's a subset of every set. So if you're talking about the empty set, I would just always use this symbol, and then you're always safe. Let's say we have a set and we want to figure out how many possible subsets there are. There's actually a mathematical way to do this, or you could actually figure out all the different possible combinations. But we'll start by figuring out the different possible combinations of a really small set, and then we'll go from there to the mathematical thing, so that if you have a really giant set, you don't have to figure out all the possible combinations. So if I have an empty set, I have no elements. So what is the only subset of the empty set? The empty set. The empty set is a subset of itself. So I have one possible subset. If I have the set A, which has one element in it, the possible subsets are the empty set, because that's a subset of everything, and the set containing A. So it's 2. And if I have two elements, A and B, I have the empty set, and I have A, and I have B, and I have A and B. 1, 2, 3, 4. And if I have 3 elements? Huh? That was your- I have 3, I can have the empty set, I can have the set A, I can have B, I can have C, I can have AB, AC, BC, and ABC. I know that's hard to read, sorry. So that's 1, 2, 3, 4, 5, 6, 7, 8. What's happening to this number over here every time? It's doubling. And the relationship to this number here is maybe a little harder to see. But we've got, as we increase the number of elements in the set by 1, the number of subsets doubles. So if you have n elements, so some number of elements,
So on that top one.
2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4, 2 to the third is 8,
So the next one is
2 to the fourth, yeah, 16. So you take your number of elements, that becomes your exponent on the number 2 to figure out how many subsets there are. Yeah. So let's say I have a huge set. Okay. This is the other thing. Proper subsets, because we have to take out the copy. Reduce it by 1. So subsets is 2 to the n, where this is the exponent. Proper subsets is that number by minus 1. So, alright, so subsets, oops, that's not a pen. 2 to the n, proper subsets, 2 to the n, and then minus 1. So I have 1, 2, 3, 4, 5 elements. So subsets is going to be 2 to the 5th. So 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So there are 32 subsets. And proper subsets is going to be 32 minus 1, so 31. My subsets is going to be 2 to the 7th, which I'm just going to go ahead and cheat. And then my proper subsets is going to be 128 minus 1. Oops. Oh, I don't know what I was just doing here. No. Okay, not too bad. It's far better to do this math than to take the 9 through 15, write them down, and to find all the possible subsets. You have to find 128 of them. And there's only 7 numbers in there. What would happen if I have a set with 20 elements? There's 1 million subsets.
Wait, how did you get that?